Kjo puna e kamerës tani më duket sikur shikoni më shumë nga drasa. Mund ta deri ku e shikoni drasën? Shikoni lapsin për shembull?
Lapsi duket, po.
Okay, u zgjidh problemi. Se ti të u zgjidh, po u zgjidh. Tani më hoq, okay. Ishte një si tip brezi i bardhë, i cili bllokon goxha nga ekrani. Okay, so for today we are just going to talk about some transforms, and these transforms that we are used to. We are used so far with Fourier transform. Then we have the discrete cosine transform. We have also Haar transform, wavelet transform. So these are all different types of transforms. And the general idea is always that if we have any signal which is in 1D, we can transform it as simply as follows. So let's assume that we see what we're looking at. So first of all, let's look at one dimension. For one dimension transform, we can write the following. Given any function f of x, we can find another function t of u. So this is the new domain, okay? This is x, this is u. And this transformation, this is expressed as this function t of u. This is equal to the summation of some terms from x equal to 0 to n minus 1. And we are assuming here that we have here n points. Okay? So this function is discrete with a specific sampling rate. We have n points, that's the idea, and we are going to add from x0 to xn minus 1, and we're going to multiply f of x with the function which is rxu. Now, this rxu, this is called the kernel, or the transformation kernel. So let me call this one transformation kernel. So this is the function which causes, now I can use the term which is not the best term to use, which is called the mixing kernel. Okay? I'm going to erase this one just for a moment, but if this was the Fourier transform, now this is any general transform, the kernel, probably remember such a term, e to the power ikx, okay? This e to the power ikx, this is the kernel which enables the transform from the x domain, which in this case, if we multiply here with f of x, this is a minus dx. Probably you have seen this one too often. We have seen this a lot. Okay, so this is the kernel. This kernel, we want to write this one in a discrete form like this. And then if we integrate here on the other side, and this integration, this has limits. Okay, so let's assume this is integrated from minus L over 2 to L over 2. And if we are integrating over x, x is in here, here, and here. Then the function that will be left, it will be a function of k. Okay. So this is the analytical expression, which you have seen this you have seen this a lot. Okay. Now this transformation kernel rxu, you can see that this is the mixing terms. So this is interchange in the terms of x and u, so that when the x with this x are correlated or element-wise multiplied with each other, we will have only u as an outcome. Okay, so this is how this will come out. Now, I can erase this part, and this was the transformation kernel. And with this transformation kernel, we can also add, give me a second, I just want to see. Okay, so with this transformation kernel, we can also construct the inverse of this kernel. So, sorry, the inverse of this transformation, which is f of x, will be equal to, now we are going to sum over the u. How many values of u we have? We go from 0 to n minus 1. And here we have here t of u. This new function, which is in the transform form domain, we multiply this one with s ux. Okay? So this is the transform, this is the inverse transform. Now, if this is the case, there are a couple of definitions that we can write regarding this. For example, here, this TU, we can write this one also as the inner product of two different operators. So we have here the inner product of a vector R and a vector F. Okay, so this is one way to represent it. Another way to represent this one is that this whole TU that we see here, we can also write this one like this. This T, this is equal, this is a vector, okay? This is a vector because it has an array of numbers. An array of numbers, that's what it constitutes, okay? And if this is a vector, we can write this one as a matrix A times the F, and F is also a vector. And now, given this, we can also, so this is equivalent to the first one. We can also have back the function F, which is an array of numbers, and this is A transpose times T, okay? So, what do we see here? We see that this specific transform, we don't know the kernel can belong to any one of these different transforms. We can write this one either by doing this type of multiplication, or we can denote it like this, where T is the transform with A times F, and the inverse is A transpose times T. Now, in principle, I guess some of us might assume the following. If we have T, which is equal to A times F, how can we get, let's multiply from both sides with A inverse. Let's multiply A inverse, because this A is a matrix, okay? With matrices, we can denote this like this, and the functions or the vectors, we can denote it with a single arrow. Now, let's multiply both sides with A inverse. Now, we see that this is going to be the identity matrix. So here we have that A inverse times T, this is going to be equal to F. Now, this F, it looks like if this is true, this means that this A inverse, this is equal to A transpose, okay? Then, if this is the case, well, we are kind of indirectly showing that A inverse is equal to A transpose, and this matrix, this is called an orthogonal matrix, okay? Orthogonal matrix, if you remember from your linear algebra courses, it's a matrix that has two properties. The first property is that each of the columns, they are orthogonal, which means that the inner product between any two columns is going to be 0. For example, let's assume that you have a matrix which has columns like this, 1, 1, and this other vector, 1, minus 1. What is the inner product between these two vectors? We know that the inner product between any two vectors, let me write it here, S1 dot product S2. So this is the dot inner product or dot product. This can also be denoted like this, S1, S2. This is the same thing. This is also written like S1 transpose times S2. Okay? Now let this be S1. S1 transpose is equal to, we write S1 transpose is, it is a column, this becomes a row. So we have 1, 1 times 1 minus 1. And we have 1 times 1, 1 minus 1, this is 0. So it looks like if this matrix A has two columns that look like this, then they are orthogonal. So the first property is that columns should be orthogonal with respect to each other. The second property that we require for a matrix to be orthogonal, or to have such that we can use in these types of transformations, the columns, they should be orthonormal. Orthonormal, it means that the magnitude of each vector is 1, so it should be normalized. Orthonormal. So the moment that any matrix A, the columns of A, satisfy these two conditions, then we call this one an orthogonal matrix. And an orthogonal matrix, it has a beautiful property that the transpose is equal to the inverse. Okay. Now, let's have a look. If this matrix A has these two columns, is the first column vector, so the matrix A, in fact, it would look like this. A would look like 1, 1, 1, minus 1. Okay, so, but the question is, when you look at this matrix A, columns are orthogonal. That's good, we confirmed it. We have two columns that are equal to 0. But are they orthonormal? Orthonormal, that means the magnitude is 1. So we find the following. We have, what is S1 dot S1? So we want to find the dot product. We denote this one also like S1, S1. At the same time, this is S1 transpose times S1. And this is going to be equal to 1, 1, like this, 1, 1 times 1, 1. And this is equal to 2. Okay? So it looks like this column is not orthonormal, so it's not, the magnitude is not 1. So in this case, we need to normalize this. In order to normalize, we write here, this is equivalent to 1 over the, let me think for a moment, this is equal to, no, actually, this is the norm, but the magnitude of any vector S1 is going to be equal to the square root of inner product of S1 with itself. Okay? So, based on this calculation, that means that the norm or the magnitude of S1 is equal to square root of 2. So, if the magnitude is square root of 2, we need to make this 1. How do we make this 1? We just multiply with this factor. This matrix 1, 1, 1, minus 1. Okay? So here, this is equal to this matrix, and this is equivalent to this other matrix. This is not an equal sign, but now we made this matrix A an orthogonal matrix. And these orthogonal matrices, what they really are, they are rotational matrices, which means that they don't change the magnitude of a specific vector, but we just rotate it in a specific domain. Okay, so this was this part, starting in this section. We just try to do, probably I can erase this part. So we just reviewed a little bit the concept of orthogonal matrices. And now we have this, so probably I can erase this. You can take a note for a moment. And the orthogonality of a specific matrix, it can also be represented like this. So for any two columns, let me write this Ci and Cj. The inner product between any Ci, Cj, this should be equal to the delta ij. The delta ij is equal to 1 when I and j are equal to each other. But it's equal to 0, so this is equal to 0 if I is different from j, and it's equal to 1 if I is equal to j. Okay, so whenever we take the inner product of a vector with itself, the magnitude should be equal to 1. So this is one way to represent an orthogonal matrix, or probably maybe the comprehensive method to represent them. So then let's come back to our transformation. So hoping that we got this, we understood this part, we move a little further. So it looks like these are the transformation, inverse transformation, again, transformation, inverse transformation using the matrices. Now, this is the one-dimensional case. We can now denote the two-dimensional case because we have some signals which the details can be stored in 2D. And in that case, so this was one dimension, then for the two dimension, everything will change slightly. So we are going to have a T, it's going to be now, this will be the transformation of the data, and this will be equal to the summation of x equal to 0 up to n minus 1, and the summation of y equal, starting from 0 to n minus 1, and we sum this over with f of xy times a kernel Now, the kernel here, actually, I could erase this part, but it's fine. So the kernel here, this is the mixing operator, which mixes x and u's. Now here, it's going to mix x, y, u, and p. Okay? So this will be the transformation. Now the inverse transform, this might be predicted from most of us. This will be like the f of xy is going to be equal to the summation of u from 0 to n minus 1, the summation of v, which is from 0 to n minus 1, similarly, of t uv. So this function here multiplied with another operator, which we can denote this one like s, which will be x, y, u, and v. Okay? Now, this is the two-dimensional representation of how one transform can be conducted. Now, let's try to draw an equivalence between the one-dimensional case and two-dimensional case. Here, this f, it was an array of numbers. Okay, so it was just a function that if we plot it, it's going to look a function like discrete data points. It can be some points here, and we want to find the specific transform. But now we don't plot them one x versus y, but now we have them related in a two-dimensional array, like we have an image. In this case, this f is not anymore a vector, but this is going to be a matrix. Okay, so the situation will slightly change, and in this case, the transformation it can be written in a different way. So we say that this transformation, which will be also a matrix, this will be equal to A times F, where F is what it was before one-dimensional, times A transpose. So this is how we can go from 1D to 2D. The inverse is the transform like this, and the matrix representation, it goes like this. And then this F, this will be equal to A transpose times D times A. So from here, this is the general idea of how we can change from one domain to the other. So one thing which is very important to notice or to be aware of is that we have this nice transformation matrices which allow us to change from one domain to the other. And the best ones that we can work with, they were the orthogonal ones which satisfy this condition. Now, this was in general. Let me have a look at okay, so what we're dealing here, what we can see from this slide, we can see that any function which is sampled at a specific rate, which in this case we have picked up just n different points, we aim to transform this one in a new domain as a function t of u or t of v. But this transform, it has some specifics, or it is one transform that we can describe different features which is hidden in the data. Now, let's see. So what we see here, actually, this operator that, for a moment, okay. Actually, the first slide, it's somewhere here, actually, which, as you can see from here, this is the Fourier transform described in the first notation that we wrote here on the board. So, for example, this is, you can all try to work this out, but it's going to be something like this. So if the function, if we have some data in X which are 1, 2, 3. So if you have some data which are 1, 2, 3, then we can sum over all the n's. But then let's say that we're going to go to the new domain, which is a capital X, and we're looking for the xk when k is equal to 1. Then if this is k equal to 1, let's see what we're going to get. We sum over n from 1 to 3. So n, well, this is a small n. Let's assume that the small n is 1, 2, 3. And let's see what the summation is going to be. We have little x at 1. x1 is equal to 1 times exponential. This is exponential minus j 2 pi k minus 1. Now, that there we see it's k minus 1, which means that k is already 1. 1 minus 1 is 0. So we get exponential to the power 0. Exponential to the power minus j 2 pi times 0. So this makes it 1 right away, right? This is then times n minus 1 times 0, because n is 1, over n. Okay, over n. That's good. But this is only the first term. So this term is for n equal to 1. Then plus the second term, this will be the second term is 2 to the power exponential of. Now, for the first case, since the k is equal to 1, which means that this is n. Now I picked up very strange numbers. Let me put this one minus 4 minus 1, because 1, 2, 3, you get really confused. This n, this is 1, 2, 3. And now here, we want to count this other set, which is counted using the k. So this is going to be k1, k2, k3. So it looks like when we find the very first element here, we have the exponential term is always going to be equal to e to the power 0, which is equal to 1. So this element is the summation of 1 minus 4 minus 1. So this is going to be equal to minus 4. So here we get equal to minus 4 because this will be continuing. So this is minus 4 times exponential of minus j 2 pi times 0 over n, whatever. And then minus 1 exponential of minus j 2 pi times 0 and so on. Then we go to the second term where k is equal to 2. When k is equal to 2, according to what we see on the slide, this is exponential of 2 pi j with a minus k minus 1. Then k is going to be equal to 1 times n is 1, n minus 1, this is 0. So this, just for instant, this gives this equal to 0 divided by n. So this makes this the x k equal to 2. This will be equal to 1 divided by n. So this is going to, no, this will be just 1. Then the second term, it will have minus 4 times exponential. This will be k is 1 times n is n minus 1, which is going to be times 1 again, divided by 3. So what we see here, this will be minus 4 times exponential of e to the power minus I 2 pi over 3. Finally, we got some non-odd number. Then this is minus 1 exponential of minus j 2 pi times k minus 1, k is 1, n is 2 divided by 3, so this is going to be minus 1 e to the power minus I 2 pi times 2/3. Okay, so the second number, it looks like in this element is going to be a complex number. Okay, so we can work this out, and we know what is the e to the power minus 2 pi over 3. We can represent this one like cosine of this angle minus plus sine of that angle. So this is how this can be represented. Okay. Now this is the Fourier transform. We can see this one on this slide. We go ahead. And that operation which is done there, we can see this one in this slide. Now with this slide, this shows this is something like a cartoon which shows how the outcomes of this expansion that we started here on the board can be done when n is equal to 8. So if n is equal to 8, you can notice that the frequencies that appear on all of these terms, there will be multiples of 2 pi over 8. Okay. So just for a moment, I know that you that are watching the class, you can. So all of these terms, so this exponential, it carries the terms which minus I is always there. You have the 2 pi, it's always there. And then we have also 1 over n, which n is equal to 8. This 2 pi over 8, this is pi over 4. Pi over 4 is 45 degrees. Okay, so you have the oscillatory patterns with a specific cosine of 45 or sine of 45. So this is what this matrix is trying to represent. It's a nice cartoon if you try to check this carefully. And what is interesting is that there is a symmetry where we can see that the coefficients for s equal to 6 and for x equal to 2, we have a symmetric situation. Now, let's move it a little further. So here, we see just the representation that we see here. We have not covered in details all of these transforms that are shown here in this slide. And this is a larger, so the previous slide we had for n equal to 8. Here, this is for n equal to 16. The coefficients which are shown here. This is DFT, discrete Fourier transform, DCT, discrete cosine transform, and the wavelet Haar transform. So that's another type of transform. And let's see what we have next. Now, whenever we do a transform, in fact, what we are really doing, we are, as we have seen before, when we did a little more detailed Fourier transform analysis, we said that we are going from the f domain to the t domain for the time, or from the time domain to the frequency domain, and we have a relationship that the width. So if you see this time frequency plane, what we see here is that the width of this. So let me think. There's a beautiful keyword which denotes the surface area. The surface area in the spectrum, and the surface area which is equal to the width in the time domain times the width in the frequency domain is called the surface area in phase space, Apsira phasora, in the phase space. And we notice that, which I guess you already know, that the smaller the width in time, which is this one, the larger the width in the frequency domain. For example, if we have a unit pulse function like this delta t minus t0, which shows that at t0 we have a 1 and 0 everywhere else, this has a width of 0 because it's a step function. Okay? Since the width is 0, then the width of the same function in the Fourier domain is infinite, or whatever it fills up the complete domain. So you can see here, the width here is unit pulse. On this other domain, this is covering the whole frequency. So it's everywhere in the frequency domain. Then, I guess these are a couple of representations of how a specific function is decomposed using Delbecq's basis function. And Delbecq is a specific wavelet, which is, you can assume that this type of wavelet is something which should look like a sine or a cosine. But now let's see this other slide. So what we see here, this is discrete Fourier transform. You can see at the top of the slide. So discrete Fourier transform, you know what the kernel is. The kernel, it was equal to e to the power 2 pi times I, the complex number, times 1 over n. So this 1 over 8 is 1 over n, times n minus 1. Okay, so this is, and we have also, so this is the kernel. Okay? And these kernels, if we plot all of these kernels, if we write them down here, and this is the element which depends on the x and on the k. Okay, so the complete kernel is this. And if we plot this in a matrix where we can exchange the, for x and k being 0, 0, 1, 0, 1, 1, and n minus 1, n minus 1, this is what we observe. And now, from the previous slide, so this cartoon that is here, if we take this one on this, if we put this on the top, we have this matrix which is 8 by 8, and we can see that the normalization factor in this matrix is 1 over the square root of 8. It is 1 over square root of 8 because if you see the first column, it's a column with 8 ones. So the magnitude over there, it's a square root of 8. So for the sake of normalization, we multiply it with the given numbers. Now, so if you, as we wrote before on the board, we said that any transform T, which is a vector, is going to be represented by a matrix A times a function f. And in this case, the function f, assume that is this one, which has a couple of ones at the beginning, and then it's full of zeros. That capital T stands for transpose, actually, this T here. And in order to find the Fourier transform of this function, we just multiply this 8 by 8 matrix with this vector, okay? And if we multiply it, we're going to see a series of numbers . So the Fourier transform, it will be, so what is the square root of 1? What is the square root of 8? It's 2 square root of 2.
Should be around 3.4.
3.4, okay.
3. Sorry, no.
Okay,
2.8. 2.8 actually.
2.8. Okay, then for a moment, let's try to multiply this matrix A with F. So if we multiply this A with F, if you put this F as a vector, we get the multiplication of a series of ones with a couple of ones alone. So that gives a 2. 2 divided by the square root of 8 is equal to what? Can you calculate this one? 2 divided by the square root of 8.
0.707. 0.7.
Okay, thanks. So this means that if this is going to be the case, then the answer will be that as you calculated it, this is going to be 0.7. And so everything comes now from the matrix multiplication. This is 0.7. Then we get 0.6 minus 0.25j. Then we get 0.35 minus 0.35j again. That's the other element. We get 0.1 minus 0.25j. We get a 0 here, okay? And then we have the 0.1 plus 0.25j. Now, probably you have seen this Fourier transform, how we take it before, but there is also one specific important element here, is that half of the elements in Fourier transform are the complex conjugates of the other half, okay? So this is 0.1 plus 0.25j, because it's the complex conjugate of this number, and then the next element is going to be the complex conjugate of this one, okay? So there is a symmetry in this is plus 0.25j, then the final element is 0.6 plus 0.25j. Now, this is the Fourier transform of, instead of this f, let's write here, this f was equal to 1, 1, 0, 0, 0, 0, 0, 0. So we had the matrix A, which was 8 by 8, and this vector is 8 by 1, and we get another vector which is 8 by 1. Now, the very first element, if you remember, when we did this Fourier transform of this signal here, we notice that the very first element, it was a summation of all of these numbers, which we can redo this again, which was equal to -4. Okay? And also here, we sum over these numbers, this is 2, but we have to multiply with the normalization factor of the matrix A, which you calculated. It was 2 divided by square root of 8, and we get 0.7. And then the rest, this is how we find them. So this was the Fourier transform. Now, let's see a couple, sorry, no, I should not, yeah, okay, let me present, let's go over a couple of more slides. So this was discrete Fourier transform. Then we come back here, and so this is discrete Fourier transform. We saw this example on the board, and this is another transform, which is called the discrete Hartley transform. And the discrete Hartley transform, it has, instead of using a kernel, which is, so everything, it changes in the kernel. So before, with the Fourier transform, it was an exponential, which was e to the power minus I times 2 pi times divided by n times n minus 1. So this was the kernel. Okay, so we used to multiply with a series of these factors. Now, in discrete Hartley transform, we have a new function, which is a function which is cosine of 2 pi ux over n plus sine 2 pi ux over n. Okay, so it's a strange function. Sometimes in some textbooks this can be called like CAS, like which is cosine and sine. So it's a summation of cosine and sine, and as an operator, it's a strange operator because you know how the sine and cosine, they are shifted with respect to each other by a value of pi over 2. So if we plot the cosine and the sine, and we add these functions together, we can observe, I did not draw this one right now, but we observe some strange features, and this feature, it can be observed, in fact, even in the second line of this matrix, because we know that cosine at 0 is going to be equal to 1, and sine at 0 is equal to 0. So that function, it starts from 0.5, and it's like a smooth version, okay? Because whenever we have the cosine at the maximum, we have the sine, it's a 0. So it will always smoothen out. It's like a smoothing operator. But this is called the discrete Hartley transform. Now, this discrete Hartley transform, it has also the separable two-dimensional kernel. So what we see here for this operator, so we call this one just as CAS, okay? This is a CAS, and in a couple of minutes, once we shut down the slide to see the board, I can write now that this discrete Hartley transform, or DHT, this has also the separable 2D kernel. The separable 2D kernel is going to be a function of x and y, u and v, and this is equal to, maybe I can write this one after a while when I will not be sharing the monitor. And so this is discrete Hartley transform. It's summation of sines and cosines, and here we see just the comparison between the DHT, the discrete Hartley, and discrete Fourier transform. So they draw some similarities. A major difference between these two can be observed sometimes at it's even a similarity actually. At the endpoints, they look very similar to each other. Not very similar. The similarity comes mostly because the sine is equal to 0. Okay, so it will be non-affecting. Now let's see another type of transform, which is also very useful, discrete cosine transform. Now, the previous two transform, the Fourier transform and the Hartley transform, they have a specific frequency resolution, and their frequency resolution is the same. With frequency resolution, we denote the delta k. Now, the discrete cosine transform, what it does, it extends the frequency resolution by a factor of 2. Okay? And in order to extend the frequency resolution by a factor of 2, what it is really doing is that the initial data set for which we want to take the discrete cosine transform. It is extended, okay? So imagine now that you have a function which has 4 data points, and then we make this one equal to 8 data points. So we extend it. But the way we extend it is that we take the symmetric with respect to the end point. So we make a, how can I say, we take the mirror reflection of the given function at the end point. Okay, that's what we do. So imagine for a moment we have a function with 4 data points, which goes like this. And then we take the mirror reflection of this, and we're going to obtain another function that is going to look like this. And for better representation, the mirror representation of this function will be these new 4 points. So let's assume that this is the f of x, this is the given data. It's not a continuous function, it is discrete for sure. Then this is the extended version. This has it has 8 data points. So this is the g of x. And then this g of x we multiply with the matrix for the Fourier transform. Okay. So here we have 4 data points for f. Then for g we have 8 data points. N is equal to 8. 8 is equal to n. Then when we apply this Fourier transform on this g of x, we get a function t, which has also 8 data points. And this t, this is equal to t1 and t2. Now, or probably it's better if we get done with the slides, but I guess everything is written on the top part of this slide. So discrete cosine transform, it has twice the frequency resolution. It extends the function from n data points to 2n data points, which means that it assumes even symmetry. And then we take the discrete Fourier transform of this new function, g2n, okay? And this is a specific example. So let's assume that we have some points, which is 1, 0, 1, 4, 9. But probably, let me stop sharing just for a moment. And before a while, actually, I stopped from writing down the separable function of the discrete Hartley transform, so DHT. For the 1D is written here. For the 2D, it's a separable kernel. And we know how a separable kernel works, okay? So we can have the kernel along the x-axis. We multiply with the kernel along the y-axis, and we get a matrix, right? We get a matrix which is n by n. And we know how to get a matrix from 2 vectors. And in this case, this discrete Hartley transform is going to look something like this. 1 over square root of n. And here we have this operator, which is CAS, which in fact is sine and cosine of 2 pi ux over n. So this is the first part, times the symmetric of this one, but now it's not ux, but it's vy. So the same thing is multiplied with 1 over square root of n, CAS cosine plus sine of 2 pi. This is Vy over n. So these are, so this is we multiply a vector which is represented by this, and by this other vector which is represented by this other vector, and we get a matrix. So this is going to be a matrix n by n. Okay? And the first vector, this is n by 1, and this is 1 by n. And now this u and v that we see, these are the reciprocal. So if we have here x and y, there is in the transform domain, if we transform all of this data by using a matrix operator A or S, so in this case this was S, we can denote this one also like this. The reciprocal of x, we denote this one as u, and the reciprocal of y, we just denote this as v. Okay, so this is the new domain. This is how they are going to look here. Now, let's see this example regarding the discrete cosine transform, which apparently it provides a higher frequency resolution. We like this higher frequency resolution because we get more details in some way. Now, let's assume that we have a function which is composed of these values, 0, 1, 4, 9, okay? So this is our function f. Then, the first step that we do when we have such a function is that we need to extend it. And in order to extend it, we just take the mirror symmetry as we did here. So we're going to get the function g, which is going to be equal to 0, 1, 4, 9, and then we get the 9, 4, 1, 0. So this is the extended version of g. And now from 4 to 1, we've got a vector which is 8 to 1. And now this is the moment that we multiply by this matrix which represented the Fourier transform. And then as a result of this vector g of x, which is 8 by 1, we get a function t, which is also composed by 8 by 1. And this is equal to, if we write this one, t1 is composed of, let's say, 4 by 1. We just, and this is the bottom half. So t1 is the top half of this transform. This is also 4 by 1. t1 is on top, t2 is on the bottom. So, but this is not all. There is also a little trick which so far we can denote, we have f, we found g, then let's call this one here, we apply the operator a on the Fourier transform, we get t. This is 4, this is 8, this is 8, and then we find t1, which has 4 elements, t1, 4, and now this t1, we have to multiply these with a couple, so we multiply with a new kernel. So we make up a new kernel, and this new kernel is going to be the following. We denote an h of u. So the reciprocal of x is going to be u. This is not a two-dimensional discrete cosine transform. And the kernel, it looks like this. It's again, if it is a sine transform, cosine transform, or Fourier transform, we are always going to see this exponential. We're always going to see this minus I, and we have also this pi. We multiply here by u, and we divide by 2n. Okay, so this is the kernel, and here, the u, it has n values, which means that here u, we have 4 u's. We have u1, u2, u3, and u4. Okay, so these will be the four values. So this is the u, and then we have to multiply them also by normalization factor, which is going to be equal to 1 over square root of 2, so it's going to be a vector, then it's full of 1's. Okay, so we normalize only the very first element. Now, this was the representation of how we extend the function. If I erase this one for a moment, and then let's see how this data will be transformed. So this is the initial data set. This is the extended version. We apply here this operator A to find the Fourier transform. And here, if we write just the first half, the top half of this T, which has 8 data points, the answer is the following. It's minus 9.9, minus 6.16, minus I, 2.56, 1.41, plus I, 1.41, and minus 0.18, minus I, 0.44. Okay, so this is, as we said, this is the top part of T1, but we are not done yet because this T1, actually, there's a better way to represent this one. Probably we can go, let me think for a moment. This is T14. From here, we just multiply S with H with T1. Okay, so this is the final answer. So it's a little tricky, but if we go over again, so actually, with the language of functions, probably it's best if we write it like this. Initially, we have the function f. Then we apply an operator, which is an extension operator. Let's call this one ex. It's a matrix, okay? Then after this extension operator, we got this, we take the Fourier transform. Let's write this one ft. So this f was 4, extension was 8, Fourier transform is also 8. After we take the Fourier transform, we find t1, t2. We crop the bottom part, we leave only t1. So let's call this one crop. Okay, we crop this Fourier transform, we crop the bottom part, take it away, or truncate. Crop is for imaging, but truncate is more a mathematical term where we cut out some part. After we do the cropping, we have this function. We multiply this with the function h, and then we multiply with this normalization factor s. Okay, so this is equal to the discrete cosine transform of f, and this is equal to this. It looks like it's a little. It has quite a few of operations to do. So only the Fourier transform. So the Fourier transform used to do only this, but this is following a couple of modifying factors, which is going to incorporate the higher frequency resolution. Okay, so this is let's say that how we take the discrete Fourier transform. Now we have other, as we said actually, we have other transforms. The only trick that we'll always have to follow is the first thing. We'll just go and look after the kernel. Okay, what does the kernel do? And the kernel, it hides or it bears a lot of symmetries that it is made for. Okay, in the construction of these filters, a lot of intuition is used, but also it's not only purely intuition. It's also the researchers that work on the filter development. It's not purely intuition. They also can predict what the output is going to be. For example, discrete cosine transform is a very good transform because since it has a cosine, that means that it's going to multiply by 1 the edges. So the edges of an image, when we apply the discrete cosine transform, we're not going to multiply them by 1. Okay, so that's something intuitive to use cosine transform when compared to the sine transform. Otherwise, we would get edge information darkened completely. So this is more or less what we wanted to cover. We can go over a couple of examples or exercises, or we can see. Meanwhile, any question that you might have? Let me try to pick up some image somewhere. So if we pick up some flower, and we may want to see actually how we can decompose or manipulate images in different domains. I like this one a lot. Save images. So this image that we picked up, no. Flower, here we have it. I'm just trying to drag and drop this one here. Okay. We got the flower. So if we just read an let's say an image, then as we read this one, since this image is colorful, we can try to, it might be best to convert this one into grayscale, and we can call this one IG is equal to RGB to gray of I. And as you can see, the image is 194 by 259 times 3. So we can convert this one in grayscale. And then from the grayscale, we can decompose this one into its coefficients by using wave decomposition, the two-dimensional wave decomposition of this image IG, the image in grayscale, using 3 levels in this decomposition and using Daubetch's wave DB4. Now, to get the detail actually what this does, let's see wave deck 2. With this wave deck 2, we can see what it does. We can see the details. So once we decompose this image into these coefficients by using the wavelet decomposition, we can use specific or levels of this decomposition to reconstruct the image back. So, for example, if this is the decomposition, we can generate another image 2, which can be written as wave recomposition 2, using the coefficients of C and S that we found above, using the Daubetch's 4, type 4, image. MATLAB is pretty busy. Then here we can have figure 1. We can show what is the image in the grayscale. Figure 2, we can show what the image looks like after we have recomposed it. So this is the decomposition here, and we recompose it back here. And figure 3, we can try to show what is the difference between these two images. So we have this IG minus u int 8. Let's make this unsigned integer 8, because now this u2, this most probably, this is double. So let's evaluate this part. MATLAB is busy. So we see that I2, which is the decomposed data set or the image, the type is double. So we can make this one u int 8 I2. So let's see what are these three figures. Okay, so this is figure 1. This is the second figure, which the second figure, it should be the recomposed image. And this is the third. Actually, the I2, we don't see this one yet, probably because the variable is double type. So if we modify this one a little bit like this, figure 2, which was here. Okay, so here we see the figure 2 again. It's the recomposed. So we got this one from IG, the grayscale of the image I. And here, figure 3, probably there is something, but we don't see it because it's we can stretch it out. Still, figure 3 is completely dark, which means that probably they are equal. So we might have a perfect reconstruction between I1 and IG and I2. We can also try to determine what is the highest value of the difference between IG minus unsigned integer 8 of I2. So let's see what is the maximum difference of all the pixels one by one, the largest possible difference between those. Let's see what we get. We get a 0. So it looks like we really have a almost perfect. Probably this should not be like this. In fact, if I remove this u int 8 here, let me make this one double, because I2 is already double. If we see this one in the workspace, here I2 is double. IG is unsigned integer 8, but let's make this one both double, and let's evaluate what is the difference between these two. Okay, we get something like 7.4 times 10 to the power minus 10. Okay, now that they are double, apparently there is a difference between those, but it's almost negligible. When we make this unsigned integer 8, of course, it might be expected to get a 0, but this gives a little more insight. Okay, so there is some difference, but it's pretty small. So now these coefficients that we have here, we can zero out a couple of coefficients. So these coefficients, we can there is another function. So we here we denote these coefficients that we want to make 0. It's wave. We select coef2, and these coefficients, the coefficients in the wavelets, they have a specific, we denote them differently. We have three major axes. One is the horizontal, the vertical, and the diagonal. So here we want to zero out the first level of the diagonal terms in the coefficients of C and S. Okay, so C and S, let's not forget what they were. They were these decomposed coefficients here, C and S, but we want to remove the first level coefficients. So we can remove the diagonal first level, and then we can try to reproduce this one, I3, where I3 is going to be equal to wave recomposition of the using NC and S using this dB4, and let's try to see if we can observe anything from figure 4, which is going to be IMSHOW I3. Let's add also this operator here, and let's see. Let's see what we find here. So we have expected error using this, expected L to be a vector, error in line 23, wave recomposition. So we could not, okay, so this is wave recomposition 2. Probably this could be the error because the data set that we're dealing with is a 2D. So let's hope that's all the error that, okay. So it looks like we recompose this image, but after zeroing out the diagonal elements in the coefficients for the first level. Now, when we talk about levels, what this corresponds to is this 3. So we have a 3-level, different levels of the wavelets. Now, the wavelets, they have the first level, which has one, it picks up specific frequencies. Then we can increase the resolution in the frequencies that we are trying to decompose the signals in a more refined version, second level. The third level, we keep dividing more and more the transform domain, okay, to increase the resolution. So we got the same image again, but let's see how much different this image is. Figure 5, we can say IMSHOW, what is the difference between the IG, the initial original image, minus unsigned integer 8 of I3. Now I3 we know what it is. It's the original image, and we have made 0, just one pair, one set of some coefficients. And this is equal to this. Let's hope everything looks good. I3, evaluate selection. Figure 5, we don't see much. Let's see if we have any. Okay, so if you see, apparently we have some differences in this initial flower. It looks like these diagonal terms, so this is the original image. So we have this one initially, then we decompose it using the Bechius type of wavelet. We zeroed out just the diagonal terms of the very first level, which has the lowest level in the, the lowest resolution in the transform domain. Okay, so I can write it also on the board, but apparently this is what it looks like. Figure 4, this is the recomposed image, the latest one. Probably by naked eye, we cannot distinguish much difference, but to be more precise, we go back and look at this difference showing like an image. The reason to show it like an image is only to see it in 2D, all the data sets in 2D. And these coefficients, we can diminish them a little more. So we can have here, actually, we can remove not only diagonal, we can remove also the vertical component, or we can start with the horizontal component, and we move the NCS1. Then we remove a little more, but now we take the vertical component in the first level. So we evaluate this section. After we zero out some more components, we say that this I3 is going to be I4, and this, let's make this I4 again, and let's plot this one figure 41, and let this be figure 51. So with all of this, we should have a more diminished image, and the difference between the original image and the reconstructed one, figure 51, let's see what we get. So figure 51, let's see if it has more information, more larger differences than figure 5. Probably it might be hard to figure it out, but it should be more, the difference should be more. Maybe qualitative analysis just by looking by eye, we cannot do such a perfect job, but we can keep up and diminish the image a little more by removing, let's say, the third order details in all of these. And let's evaluate this again. So we zeroed out some more terms, okay? And then we have here I4, let's call this one I5. And this is also I5. And I'm sorry, in the previous case, apparently we made a mistake. So what it was I4, so I had taken the difference, sorry, 51. Let's consider this one image 51.1. That's why we did not see a huge difference. So we are redoing what we did before a while. Let's see if qualitatively, just by looking by eye, if there is a huge difference between these two. It looks like it's more different because we see a sharper, a larger difference here in this part. But now, so we redid in a better way what we did before. Now this I5 is the image which is reconstructed after we have made more zeros in these coefficients. So this is I5, let's make this also I5. Then this figure is going to be figure 42. This will be figure 5.2, section, the second part. I5, we have evaluated the selection. Okay, so it looks like this flower is completely, we have removed a lot of features. And figure 5.2, this is the difference of the original image with the new one. So this is, at the first part of the course, we started with the mathematical modeling, okay, where we talked about orthogonal matrices and some other properties. We also discussed how different transformations can have different kernels, and that matters a lot when we formulate them, and even when we want to write the code from scratch for all of these transforms. And just in this last part, we just went over a couple of, just to show actually how we can decompose these images at different levels and playing with the coefficients. And actually, this C, these coefficients C that what they are, this is what C is. So C, if we see C actually, which was applied here for wave deck, for the decomposition of the original image, we see that we have some, first of all, it looks like it's a series of numbers, it's a vector, which is composed of 55,590 different numbers. Now, let's see the original image, the I, it was 194 times 259. It looks like we get 50,000. The size of C is 55,590 divided by the answer. It looks like that's not correct. Yeah, it is. Okay. So C. Then, so apparently this is almost to all the pixels, the coefficients that are allocated using this type of wavelet, it's almost equal to the number of pixels. But this is only the C. The S, let's check what is the size of S. It's 5 by 2. So apparently the S is a little more elegant type of. So this is what the S looks like. The matrix which is received after we decompose everything, which means that most of the coefficients, they are hidden in the coefficient in the C vector, in this vector C. Now, if we have, do you have any question so far? If not, we can stop.